In this video, we're going to work example problems involving the definition of the derivative. So right now, we're just talking about the pure fundamental definition of the derivative. And so the derivative is a pointwise property. The derivative is with respect to a single point at a time within the domain of a function. So you've got some function f of x, and with the derivative, you're asking the question, what is the derivative of f of x at some point a within the domain of the function? And then you could ask, okay, what's the derivative of f of x at some other point b within the domain of the function? So at the moment, we haven't started talking about the idea of the derivative as a function, in which you've got some function f of x, and you're asking, what is the derivative of f of x in general? What is f prime of x? To where with f prime of x, you get some other expression of x. You start with an original expression of x for f of x, and you get this new expression of x that represents the derivative. So you could graph this expression and then overlay a graph of the original function and compare the function graph to the derivative graph. You could think about the idea of the differentiability of the original function. And one way to analyze differentiability is by analyzing the derivative graph. No, right now we're just talking about the pure fundamental definition of the derivative at a point. What does the derivative of a function mean? Okay, and so what we talked about was that the general overarching, complete general overarching definition of the derivative is, so you first write out the difference quotient of the function with respect to a specific point a within the domain of the function. Then to get the derivative, you take the limit of the difference quotient as the denominator approaches 0. So what the difference quotient is referring to is, you've got some function f of x with some point in the domain of the function with x coordinate a and y coordinate f of a. This point on f of x we'll call point P. And the difference quotient is just the average rate of change of the function from point P to any other point on f of x, as long as it's not point P. So this point could be to the left of P, to the right of P, it doesn't matter. So let's choose some arbitrary point Q. And so again, point Q can be any point, so its coordinates we'll just say are x, and then the y coordinate is f of x. And the average rate of change of a function between 2 points on the function is just the slope of the line that connects those 2 points. So the slope of this line PQ going from P to Q is the delta y divided by the delta x. So this delta x and this delta y. And so the difference quotient here, if we use the notation that's laid out as shown, the difference quotient is, so the delta y is f of x minus f of a over, and then delta x is just x minus a. There's the difference quotient. Now to get the derivative, we just take the limit of the difference quotient as the denominator approaches 0. So that would be as x approaches a. And that's the derivative of this function, f of x, at point a, at some point a. And so what the derivative ultimately means, once you take the limit of the difference function, is, so it's giving you the slope of the line PQ, so the average rate of change of the function from point P to point Q, but as point Q gets infinitesimally close to point P on either side of P. And so since you're infinitesimally close, then we no longer refer to this difference quotient with the limit applied as an average rate of change of the function from one point to another. Instead, we refer to it as an instantaneous rate of change of the function at point P, or at the x coordinate a. Okay? Now, but what we saw was that there's different ways that you can formulate the derivative, because there's different ways that you can set up the coordinates of point P and point Q. And create the difference quotient and then take the limit of the difference quotient. So this is one form of the definition of the derivative, but you could also, so you could still have the coordinates of point P be a comma f of a, but for the coordinates of point Q, you could say that the delta x between P and Q is h. So h is just the distance, the x-coordinate distance of point Q from point P. So that would mean that the x-coordinate of Q is a plus h, and the y-coordinate of Q is f of a plus h. So the difference quotient is f of a plus h minus f of a all over h. And so to get the derivative, you take the limit as the denominator of the difference quotient approaches 0 of the difference quotient. And what you get is just another form of the exact same derivative. Okay, now we saw a third form where you could remove a and f of a for point P and instead call the x-coordinate of point P x1. So the y-coordinate is f of x1, point P, and the x-coordinate of point Q x2, and then the y-coordinate of point Q would be f of x2. And so what results is you've got the distance of the x-coordinate from point P to point Q is x2 minus x1, which you can just call delta x. And then the y-coordinate distance of point P from point Q is f of x2 minus f of x1, which you can just call delta y. So now the difference quotient is delta y divided by delta x, and the derivative is you take the limit as the denominator of the difference quotient approaches 0, so as delta x approaches 0. And you get the derivative, and in this case, this is f prime of not a, but of x1. So that's the three forms of the precise fundamental definition of the derivative that we looked at in this section. They all mean the exact same thing. They're just viewed from different perspectives. Okay. So the first question says, find the slope of the tangent line to the curve y is equal to x minus x cubed at the point 1, 0. And we're going to do this first using definition 1, it says, and then second using equation 2. Okay, so first of all, we know that the slope of a tangent line to a curve is defined to be the derivative of the curve at that point. That's the definition of the slope of a tangent line to a curve at a point, defined by calculus, defined by mathematics. So now, what are they talking about here with use definition 1 and then use equation 2? This is just in reference to the different forms of the derivative that we just talked about. For definition 1, they want us to use this form, and then for definition 2, or equation 2, they want us to use this form. Okay, so starting with this form, we've got, so let's just write out this limit. We have f of x, and we can get f of a because f of a is just y of a, that's a minus a cubed. So, okay, the limit as x approaches a of, so f of x is just x minus x cubed, then minus f of a, and then over x minus a. So you've got x minus x cubed minus a plus a cubed. Okay, so let's see. We've got, so x cubed plus a cubed plus x minus a. And so, okay, we know that the sum of two cubes, so x cubed plus a cubed, is, you've got x plus a times x squared minus ax plus a squared. And let's see, so think I messed this up. This should be a cubed minus x cubed here. So a cubed minus x cubed, right? Minus x cubed and then plus a cubed. So a cubed minus x cubed is difference of two cubes. You've got a minus x and then a squared plus ax plus x squared. So, okay, we've got the limit as x approaches a of, now let's take a minus sign out here. So you get x minus a and then a squared plus ax plus x squared over x minus a. So there we go. Now we've got the limit as x approaches a of minus a squared plus ax plus x squared. So now plugging in a, we get minus a squared plus a squared plus a squared. So minus 3a squared. And actually, we didn't even need to do this. I forgot they had given us a point, so I could have just plugged in a is equal to 1 from the beginning. But this is fine. So plugging in a is equal to 1, we get minus 3. Okay, now using equation 2, using this formula, we've got, so, okay, I'll go ahead and plug in 1 here just to make it easier. So the limit as h approaches 0 of f of 1 plus h is what? What is y of 1 plus h? You get 1 plus h minus 1 plus h cubed, and then minus, and what is f of 1? 1 minus 1, so just 0. Okay, all over h. So, okay. The limit as h approaches 0 of, let's expand this out, and we get 1 plus h, and then times 1 plus h squared is 1 plus h plus h. So 1 plus 2h, and then plus h squared. Okay, so now the limit as h approaches 0 of, you've got 1 plus h minus, and then 1 plus 2h plus h squared, and then plus h plus 2h squared plus h cubed. So, okay, here you've got 1 plus 3h plus 3h squared plus h cubed. Okay, all over h. So you've got 1 plus h minus 1, so the 1 subtract out. So then h minus 3h is minus 2h. So this is minus 2h minus 3h squared minus h cubed. So, okay, now we can factor out a minus h. So you get 2 plus 3h plus h squared. So you've got minus 2 plus 3h plus h squared. So now plugging in 0, you get minus 2. So, okay, we had, this was minus 3a squared, and now this is minus 2. Okay, now part B, find an equation of the tangent line in part A. So it's the same slope for definition 1 or 2, right? So just both the derivative, but they want us to now find the equation of the tangent line. So Yeah, we've got the slope of the tangent line, and we've got a point on the tangent line. So point slope, use point slope form from algebra. So y minus y1 is equal to m times x minus x1. So y is equal to minus 2x plus 2. There you go. Okay, now graph the curve and the tangent line in successively smaller viewing rectangles centered at 1, 0 until the curve and the line appear to coincide. All right, so this is part B is minus 2x plus 2. And now, okay, so let's look at the zoomed out graph first. So here's minus 2x plus 2, and then here's x minus x cubed. So it's the tangent line to the curve x minus x cubed at the point 1, 0. Okay, now we zoom in a little bit more. Okay, now let's continue to zoom in. We'll start to center the point 1, 0 in the middle of the screen. Okay, there we go. So the curve and the line are starting to really mesh up well. It looks like they're pretty much coinciding once you go out about this distance. Let's keep zooming in. Okay, so now they're really starting to coincide well for a larger distance. Now let's zoom in even more. All right, now they're right on top of one another. We can't even see the original curve, the x minus x cubed. And you can see how zoomed in we are. It goes from 0.996 to x is equal to 0.996 to x is equal to 1.003. If a rock is thrown upward on the planet Mars with a velocity of 10 meters per second, its height in meters after t seconds is given by this function here. So now let's first find the velocity of the rock after 1 second. So you're on the planet Mars, you're on some surface location. You've got this rock that's just thrown up, straight up. So it's going to be following this vertical path, this vertical line with coordinate h. So at any time t, what's output is the coordinate location of the rock along this line. And so at t is equal to 0, you can see that h is equal to 0. And so that's going to be ground level. Well, I guess it would be the height of the person's hand, so somewhere like here. So I guess you could have a slight negative distance below the person's hand, but I think they're just trying to keep this simple for illustration. So we'll put the origin at the ground. So there is no negative h values. So what h is going to do is, as time increases, h is going to increase, get to a peak, and then decrease. If you plotted h versus time, you're going to get something like this. It's going to start off at ground level and then do, right? So, okay, what is the velocity of the rock after 1 second? So with the way they're stating this question, they're asking what is the velocity of the rock at time t is equal to 1 second. So at this instant in time, if you took a picture of the rock after 1 second after it was thrown, at that moment, what's the velocity of the rock? Well, in that case, they're asking for the instantaneous velocity of the rock, right? Which we know is the definition of instantaneous velocity is the derivative of the position function, the corresponding position function curve. This is the position function curve. The position function is the position of something with respect to time. So we need to get the derivative of this function at time t is equal to 1 second. So, okay, we'll use we can use whatever definition of the derivative we want. Let's just go ahead and use this form. So, okay. The function evaluated at a plus h. So a is equal to 1. And they're actually, in part B, they're asking us for the velocity when t is equal to a in general. So let's just go ahead and do this from the start, just in general. Leave a just as a variable. So, okay, what is f of a plus h? That's h of a plus h, which is, so 10 times a plus h minus 1.86 times a plus h squared. So 10a plus 10h. So, okay, 1.86 and then a squared plus 2ah plus h squared, and then so 10a plus 10h minus 1.86a squared, and then so 2 times 1.86, 3.72, so minus 3.72 AH, okay, and then minus 1.86 H squared. Okay, now H of A is 10A minus 1.86 A squared. Okay, so H of A plus H minus H of A is, so, okay, the 10A subtract out, and you're left with, so, all right, 10H, the minus 1.86 A squared subtract out, so minus 3.72 H minus 1.86 H squared. So, okay, we can factor out an H from here and get, so, okay, now this is 3.72 AH. So factoring out an H, we get 10 minus 3.72A minus 1.86 H. So the limit as H approaches 0 of H of A plus H minus H of A all over H is equal to, so the H's are going to cancel, and you're going to be left with the limit as H approaches 0 of 10 minus 3.72 A minus 1.86 H. So plugging in 0 for H, you get 10 minus 3.72 A. So H prime of A is equal to 10 minus 3.72 A. There you go. So now, what is that's the answer to part B. So what's the answer to part A? Well, you just plug in 1 here. So H prime of 1, and that's, so 10 minus 3.72, so 6.28 meters per second. Okay, now C, when will the rock hit the surface? So we want to solve for when, in that case, when does H equal 0? Now, H equals 0 when T is equal to 0. That's true, but there's going to be another point when H equals 0, right? We want to find this time. They're asking for a time here. So let's just set the function equal to 0 and solve. So 10 minus 1.86 T squared is equal to 0. So factoring out a T. So T is equal to 0 is one time when the H is equal to 0, but another time is when 10 minus 1.86 T equals 0. So 1.86 T is equal to 10. So T is equal to 5.38 seconds. Okay, now with what velocity will the rock hit the surface? Well, all we do there is just plug in this time into the velocity derivative. So it's just that A is equal to 5.38 here. So 10 minus times this minus 10 meters per second. So this is, yeah, part D is, this is C. Part D is H prime of 5.38 is minus 10 meters per second. So that just means that it's 10 meters per second, but going in this direction, since this is the positive H direction. And that makes sense, because if we're not, if we're kind of assuming this ideal scenario with no air resistance, and it's just pure gravitational energy transfer, then the initial velocity was 10 meters per second, not the initial height. So when t is equal to 0, the initial height is 0, but the initial velocity is 10, right? You plug in 0 here. And so we would expect then, with no like air resistance, just this perfect energy exchange, the speed drops all the way to 0, then comes back down and goes all the way back to where it started, which was 10. The graph of a function f is shown. Find the average rate of change of f on the interval from 20 to 60. So from 20 to 60, what's the average rate of change of the function? So by average rate of change, what's being referred to is it's the change in output with respect to corresponding change in input. So the function, in that sense, the function decreases here. The output is decreasing as the input increases. Here, the function is increasing at like a steeper rate as the input increases. So on average, what's the average rate of change of the function over this interval from 20 to 60? Well, you get that by determining the slope of the secant line that connects the endpoints of the interval. So the slope of this line is the average rate of change of the function over this entire interval. So, okay. The delta x from 20 to 60 is, so 60 minus 20. And then the delta y is, you've got, let's see, 200, so 300. So 300 here, and then 700 here. So 400 divided by 40. So 10. Okay, part B. Identify an interval in which the average rate of change of f is 0. Well, okay, from x is equal to 10 to x is equal to 50, right? Even though the rate of change of the curve throughout this interval is not 0, except perhaps here, on average, the average rate of change from x is equal to 10 to x is equal to 50 is 0. So from 10 to 50. Which interval gives a larger average rate of change? So yeah, this was 10. Okay. Which interval gives a larger average rate of change, from 40 to 60 or from 40 to 70? So from 40 to 60 or from 40 to 70? Well, it's going to be from 40 to 60. It doesn't matter that you have a bigger interval here, because from 40 to 60, you've got this, it's pretty steep. Now, if going from 60 to 70, it either stayed just as steep or perhaps got even steeper, then you would say on average, like this region then would increase the average from 40 to 60. But going from 60 to 70, this is going to decrease the average from 40 to 60 for sure. Okay, compute f of 40 minus f of 10 over 40 minus 10. So, and what does this value represent geometrically? Yeah, I mean, this is the difference quotient. The difference quotient is the average rate of change of a function over an interval. And in this case, as far as from the perspective of the derivative, the point of interest is 10, the first point. So f of 40 is 200. F of 10 is 400. And then 40 minus 10 is 30. So that's minus 200 over 30 minus 20 over 3. And this is just the slope of the line going from x is equal to 10 to x is equal to 40. It's negatively sloped, right? That's why we get a negative. It's the average rate of change of the function over this interval. All right, for each of these problems, we just want to find f prime of a. And we can use whatever definition of the derivative we want. And for the moment, we'll still just focus on one of these two. We'll use the delta y over delta x definition later. So let's just go ahead and use this definition to start. So f prime of a is equal to the limit as x approaches a of f of x is just 3x squared minus 4x plus 1, and then minus f of a. So 3a squared minus 4a plus 1. And then all over x minus a. So you've got 3x squared minus 4x plus 1 minus 3a squared plus 4a minus 1 all over x minus a. So, okay. These two cancel, and you're left with, so 3x squared minus 3a squared, then minus 4x plus 4a over x minus a. So the limit as x approaches a, and then we can factor out a, let's see, you've got 3 times x squared minus a squared, and then minus 4 and x minus a. Okay. So now we have a difference of two squares. So x plus a, x minus a, and then 4. Okay, so now we can factor out an x minus a. So you get x minus a, and then 3 times x plus a. So 3x plus 3a, and then minus 4 times 1, so just minus 4. Okay, so the x minus a's cancel, and we're left with 3x plus 3a minus 4. So as x approaches a, you get 6a minus 4, which is f prime of a. Okay, so here let's just go ahead and use the same form. Why not? So f prime of t is the limit as t approaches 0 of, so f of t minus f of a all over t minus a. Okay, so the limit as t approaches 0 of, we can create a common denominator here. So if you multiply this by a plus 3, and then this by t plus 3, all over t plus 3, and then t minus a. Okay. So you've got 2at, let's see, 2at plus a plus 6t plus 3 minus 2at plus 6a plus t plus 3. So 2at plus a plus 6t plus 3 minus 2at minus 6a minus t minus 3. So the 2at subtract out, the 3 subtract out, and we're left with minus 5a plus 5t. All right. So let's see. Minus 5a plus 5t, and then t minus a. Okay, so we've got the limit as t approaches 0 of Take out a 5. Okay. Okay, so the t minus a's are going to cancel, and we're going to be left with t plus 3, a plus 3, and then, okay, so as t approaches, this should be t approaching a. So as t approaches a, the limit approaches this. So there is f prime of a. Okay, here let's go ahead and use this form. Why not? So, okay, f prime of a is equal to the limit as h approaches 0 of, so f of a plus h, substitute a plus h for x, 1 minus 2 a plus h is 1 minus 2a minus 2h. So 1 minus 2a minus 2h, square root of that, minus f of a all over h. Okay, so now let's multiply this by 1 in the form of the conjugate of the numerator. So 1 minus 2a, square root of 1 minus 2a minus 2h, plus the square root of 1 minus 2a all over all right, so here we get, when you have a minus b times a plus b, the result is a squared minus b squared. So you're left with, so this squared is just 1 minus 2a minus 2h, and then minus b squared is 1 minus 2a. And so we can simplify this. So 1 minus 2a minus 2h minus 1 plus 2a. So 1 minus 1 is 0. Minus 2a plus 2a is 0. So minus 2h in the numerator. And then in the denominator, you've got okay, so the h's cancel, and we're left with, so okay, so now plugging in 0 for h, you get the square root of 1 minus 2a plus the square root of 1 minus 2a is 2 square root of 1 minus 2a. Okay, so the final answer is, there's f prime of a. The cost in dollars of producing X units of a certain commodity is given by this function, this cost function. A cost function is it's a cost to produce X amount of units of something. So if you're going to produce 10 units of this commodity, it's going to cost, just plug 10 in here. If you're going to produce 50 units, then the cost to manufacture is going to be C of 50. Okay, find the average rate of change of C with respect to X when the production level is changed from 100 to 105 units and from 100 to 101 units. So average rate of change. What that means is we want to do, so that's the difference quotient, right? So for part 1, you've got C of 105 minus C of 100 over 105 minus 100. So, okay, we've got, let's see, so 5,000 plus 10 times X plus 0.05 times X squared. Now let's save this as equation E. So now E with X equal to 105. 6601.25. And now we can just go ahead and do minus. Okay, now divided by 5. So 20.25. 20.25. Now, what are the units here? That's dollars per unit, right? So what this means is that the average increase in the manufacturing cost going from a production from 100 to 105 units is about $20.25 per unit for each of these units that you're producing. These additional units past 100. Now, if we do this going from 101 to 100, well, we're going to expect something similar, but what we're going to get should be more reflective of the derivative C prime of 100. So, okay, we've got, let's see, 101, then minus 100, then divided by 1. So, okay, $20.05. So it's similar, but a little bit different. Okay, now find the instantaneous rate of change of C with respect to X when X is equal to 100. This is called the marginal cost. And where this comes from is you've got a bunch of data points. There's a lot of history, years of history of this plant manufacturing these products. And so they can do a curve fit to all of these data points. So you get this fully continuous function where you could plug in X is equal to any number, 100.0032. You can't actually produce 100.032 units, but it's just a continuous curve fit here. So, okay, to do this, we need to use the derivative, and we'll go ahead here and use this form of the derivative. So the form that's most reflective of a change in Y with respect to change in X. Okay, so put this here. And so remember that this here is, what's kind of confusing about this form is that you lose the clear information about point A. This is still F prime of, in this case, A is X1. That's the only thing that's kind of confusing about this form. So we're given X1. X1 is going to be 100. That's our point of interest. We're computing the derivative at X is equal to 100. That's X1. So, okay, F of X1, we can easily get F of X1. That's, let's see, $6,500. Okay, so, all right, so you've got F prime of 100 is equal to the limit as delta X approaches 0 of, okay, so F of X2, you've got 5,000 plus 10X2 plus 0.05 X2 squared, and then minus F of X1, so 6,500, and then over X2 minus X1, so X2 minus 100. And so now, but as delta X, so this is as X2 minus X1 approaches 0. So X2 minus X1 approaches 0 when X2 approaches X1. So X2 approaches 100. Okay, so we've got the limit as X2 approaches 100 of, so 0.05 X2 squared plus 10 X2 minus 1,500 over X2 minus 100. So, okay, what we've got is, this is 5 divided by 100 here. So we can So this would be, let's see, 1 over 20. So multiplying this by 1 in the form of 20 over 20, you get x2 squared plus 200x2 minus 30,000. And then 20 times x2 minus 100. Okay. So now let's see if we can. So 20 plus 100 times x minus 30,000. This is x squared. So x minus 100 times x plus 300. So, okay, we've got so x minus 100, x2 minus 100, and then x2 plus 300. Okay, so we're left with, okay, x2 plus 300 over 20. So now as x2 approaches 100, this approaches 400 over 20. So 20. So the answer here is $20 per unit is the instantaneous rate of change, the marginal cost of this cost function at x is equal to 100. So it's pretty close, right? Which makes sense. We would expect even the derivative to be close to these average rates of change that are with respect to x1 is equal to 100. The quantity of oxygen that can dissolve in water depends on the temperature of the water. So thermal pollution, like global warming, influences the oxygen content of water. The graph shows how oxygen solubility S varies as a function of the water temperature T. What is the meaning of the derivative S prime of T, and what are its units? So S prime of T, so S is the solubility of oxygen in water. So S prime of T is just the instantaneous rate of change of solubility with respect to temperature at a specific temperature. So at like 24 degrees Fahrenheit, S prime of T or S prime of 24 is just, for the slightest increase in temperature, what's that going to do to the solubility? Or for the slightest decrease in temperature, what's that going to do to the solubility? Either way. And the units are going to be milligrams per liter per degree Fahrenheit. So milligrams per liter degree Fahrenheit. Because if you increase the temperature a little bit, like by a degree Fahrenheit, what's that going to do to the solubility in milligrams per liter? All right, now estimate the value of S prime of 16 and interpret it. So they don't give us a function here. We're just going to estimate what S prime of 16 is. And we can do that by just computing the slope of the tangent line between these 2 points. That'll give a decent estimate. So what's the slope of this line? Right, that's going to be pretty close to the slope of the line that's tangent to the point at t is equal to 16. So, okay, you've got, and this is, what is this? This is the average rate of change of S over the interval from 8 to 24. So we're saying that S prime of 16 is approximately equal to S of 24 minus S of 8 over 24 minus 8. So S of 24, let's see, and S of 8. So let's see, we've got 1, 2. So, okay. So 8.5 for S of 24. And then S of 8 is about 12.5. Then all over 16. So 8.5 minus 12.5 is minus 4. So minus 4 over 16, that's minus 1/4. So S prime of 16 is approximately minus 1/4 milligrams per liter per degree Fahrenheit, which from a practical standpoint, you could say that, okay, when the temperature is 16 degrees Fahrenheit, if you increased the temperature by an extra degree Fahrenheit, then the solubility of the water is going to decrease by a fourth of a milligram per liter. Or if you decrease the temperature by a degree Fahrenheit when the temperature is equal to 16 Fahrenheit, then the solubility of the water is going to increase by about a fourth of a milligram per liter.